Hello everyone, I'm Mahnoor and today we will be starting off with the chapter of kinematics. Now this entire chapter is quite important when it comes to the world of Newtonian mechanics because here we will be talking about motion and how it can be studied both graphically as well as numerically. But before we can go any further, we should first understand some fundamental terms that we will encounter time and time again in this entire chapter. You can think of these as like the ABCs of this entire chapter. So let us begin with this object, like this blue ball over here, being sent on a journey from a point A all the way to a point B. Now suppose that this object covers a winding path like the one shown here. Now I ask you this. What if I wanted to find out how much length this moving object covers during this journey? Well, you might wonder that what we could do is focus on the length of this path that the object covers, highlighted in purple over here. In that case, what we're doing is measuring the distance that the object covers. It is the length of the path covered by a moving object. Clearly, we can see that if the object were to change its path from this purple one to, let's say, this red one, while maintaining the same starting points A and B, we still get a different value of distance. And so it makes sense to conclude that distance depends on the path covered. Let's consider another scenario where we have the same object being sent on yet another journey from point A all the way to a point B. But this time, suppose that the object covers a straight line instead. In that case, there is only one unique path that the object can choose, directed from A to B, as shown through the red arrow over here. In that case, what we're doing is measuring the shortest path covered by a moving object from one point to another. And that's what we call displacement. Do note here that since the shortest path between 2 points will always comprise of one unique path, we can conclude that displacement only depends on the starting and end points rather than the path. Since distance is path dependent like we just concluded, it makes sense to conclude that it needs only a numerical value to express its magnitude. And so we decide that distance is a scalar quantity. On the other hand, displacement depends on the starting and ending points, like we just discussed. So it not only needs a magnitude, but also a direction as well. In that case, displacement can be described as a vector quantity. Now, at this stage, we have defined distance and displacement in order to help us describe the path a moving object can cover. But there's a catch. We can only use these quantities once the journey from A to B is complete. What if we wanted to focus on the motion of the object while it is still in transit or while it is still in motion? In that case, what we could do is simply see how the amount of path covered by a moving object changes with every equal interval of time. You can think of these equal intervals of time as these segments that we've drawn over on the purple path as well as the red path. So how do we go beyond this? Well, what we can do is measure the speed and velocity of the object. Speed is defined as the rate of change of distance, or the distance covered delta t per unit time, or divided by delta t, a time interval. On the other hand, velocity can be defined as the rate of change of displacement, or the amount of displacement delta s covered per unit time, or delta t. Since distance and displacement are scalar and vector quantities respectively, it's easy to decide that speed is a scalar quantity while velocity is automatically a vector quantity. One other additional thing that we can analyze is how velocity is changing with respect to time for any moving object. In that scenario, we define acceleration as the rate of change of velocity. And the formula is presented here as delta v divided by delta t. This change in velocity can be expressed as a final velocity v minus an initial velocity u. Now, when it comes to a change in velocity, it implies that we're talking about two kinds of changes. Either the object would speed up or it would slow down. If the object is speeding up, then we're talking about regular acceleration where velocity increases, and there the value of acceleration is always positive. On the other hand, if the object is slowing down, that's when its velocity is decreasing, and this time acceleration will be negative, and that's what we call deceleration. And so we have reached our first checkpoint where we have discussed all the ABCs that we need in order to discuss further things about kinematics. And the quantities that we've discussed are as follows. Distance, defined as the length covered by a moving object. Displacement as the shortest path covered from one point to another. Speed as the rate of change of distance. Velocity as the rate of change of displacement. And then finally, acceleration as the rate of change of velocity. Thank you.